Assalamualaikum and a very good day to you all. My name is Associate Professor Dr. Ahmad Umaidi from University Malaysia Perlis. Uh, in this today's video, I'm going to talk about chapter 17, flat and round bed drive from Shigley Mechanical Engineering Design textbook. Okay, for those who have textbook, you can open the textbook Shigley Mechanical Engineering Design. Okay, in chapter 17. Okay, so let us begin. Okay, for modern and for modern flat drives consists of a strong elastic core surrounded by an elastomer. This drive has distinct advantages over gear drive or V-belt drive. A flat belt drive has efficiency about 98%, which is about the same for a gear drive. Okay. On the other hand, the efficiency of a V-belt drive range about 70 to 66%. Flat belt drive produce very little noise and absorb more torsional vibration from the system than either V-belt or gear drive. Okay. When an open bed drive is used, the contact angle found to be pi d equals to pi minus 2d. You can see the equation. Now, first of all, let's just recap what is the different images from flat drive and round bed drive and also V-belt drive. Okay, we just open the Google images. See here. Okay, flat belt drive. Okay, so this is the images of flat belt. Okay, you can see this is the flat belt. Okay, you can see the, of course, the geometry is flat. Okay, then see round belt drive. This is a round belt drive. Of course, the geometry is round. Okay, you can see the geometry is round. And last one is V-belt drive. Okay, V-belt drive, it has the V shape. You can see here, this is the V shape. Okay, it has it uses. Okay, okay, so let's see the equation. Pi d equals to pi theta d equals to pi minus 2 sin power negative 1 d over d per 2c. Okay, so always repeat the full name of the equation, like d is the diameter of large pulley, d is the small pulley, small d is small pulley, c is center distance, theta is angle of contact. Okay, you see the picture. Where is the picture? Okay, where is the picture is given in another okay, figure 17.1a. Figure 17.1a, you see the picture here. This is the picture, figure 17.1a. Okay, have a small here you have a small pulley, another one is a large pulley, both connected by a center distance called c. Okay, c, this is the small diameter, this is the large diameter, and then they have a angle of contact here, theta. Okay, this is the theta. So the equation equation is given by, okay, angle of contact theta d equals to pi, okay, pi minus 2 sin negative 1, okay, negative 1 d over small d over 2c. Okay, 2 is the center of this, and this is the equation. Another one, pi plus. The difference is plus and minus, remember it is just theorem Pythagoras equation by okay like okay theorem Pythagoras uh, okay like theorem Pythagoras equation. You should remember this form is from theorem Pythagoras when you learn in your mathematics class. Okay, so like that. So L is the length of the belt, meaning that the belt connected by a pulley. This kind of pulley. This is the pulley. Pulley 1, here 1, and pulley number 2, and the length of the belt. If you cut open, and this is the length of the belt, L. Okay. So you have the length of what is the required length for the belt. Okay. The similar set of equation can be derived for the cross belt in figure 12 2b. Okay, what is the cross belt? We see first the cross belt. Just about to recap to you. This is the cross belt. Okay, let us Google it. Cross belt drive. Okay, this is images for cross belt drive. Okay. Remember, when you are learning what you don't understand, just Google it. Okay, this is a modern time. You can just Google what you want to do. Okay, what you want. You can get all the pictures, all the information from Google. Okay, this is a cross belt drive. Okay, for belt length from the cross belt drive is found to be L equals to 4C power 2 minus D plus D power 2, okay, plus 1/2 D plus D theta. Okay, so okay, from Fairbanks, from the book Mechanic of Belt Drive, ASP paper number ni, you can Google the book. If you are interested in this, you can Google the book. You can find the paper from Mr. Fairbank. Okay, he explained that flat by theory in the following way: a change in tension due to friction force between the belt and pulley will cause the belt to elongate or contract. Okay, got to elongate or contract. Okay, elongate or contract, and move relative to the surface of the pulley. This motion is caused by elastic creep and is associated by sliding friction as opposed to static friction. Okay, the action of driving pulley through that portion of angle of contact that is actually transmitting power is such that the belt move more slowly than the surface speed of the pulley because of elastic creep. Okay, the term called is elastic creep. What is elastic creep? We just Google it. Elastic creep in belt drive. Okay, just some explanation. There are some explanation by other YouTube explanation which is we can see. Okay, definition: when the belt move over the pulley to transmit the power, the tension of the right side is more than the tension to the slack side. As the belt material is elastic, it elongates to the tight right when the slide, then on the slack side, resulting in unequal stretching on the two sides of the drive. Therefore, the length of the belt received by driving pulley is more than the length of the belt that move off the driving pulley. On the other hand, length of the belt received by the driving pulley is less than the length of the belt that move off the driven pulley. Hence, the belt must break forward slightly relative to the driven pulley rim. Okay. Okay, that's some of the definition of elastic creep. Okay, so which travel forward is transmitted on the either arc. For the driving pulley, the belt first contact with pulley with tight side tension F1 and velocity V1. But okay, just take note what is the definition of F1 and V1, because you may find it in other in other in this many in this literature lah. Find one F1 equals to velocity. Okay, F1 equals to tight side. Okay, just take note of it. Then the belt then pass through the idle arc with no change in F1 or we want it no change in tight side tension and also velocity. Then the creep or sliding contact begins and the belt tension changes in accordance with friction forces at the end of effective arc. The belt lift with the pulley with a loose side tension. Okay, of course the belt, any belt have a tight one and another one is not loosened one. Okay, has a contrast lah, upper and lower. Okay, at the end of effective arc, the belt lift the pulley with loose side tension and reduce speed V2. Okay, okay. Mr. Fairbank used this theory to express the mechanics of belt drive in mathematical form and has verified the result by experiment. His observation include the finding that substantially more power is transmitted by static friction than sliding friction. He also found that the coefficient of friction for a belt having a nylon core and leather surface is typically 0.7. The friction value is 0.7, but that equivalates by 0.1 by employing special surface finish. Ideal is 1.0. Okay, meaning no friction, but nothing is ideal. So if we apply some surface finish, it will come more less friction. Okay, so our model, we assume that the friction force on the belt is proportional to the normal pressure of the slide contact. We first seek a relationship between side tension and slide tension similar to the band of brake, but incorporating the consequence of movement, the centrifugal tension in the belt. Figure 17.6, we see a free body. Okay, this is 17.6. Okay, we see a free body of small segment of the belt. The difference force ds is due to centrifugal force. Okay, the end. Okay, the end is the normal force between the belt and pulley. Friction the end, or the shearing due to friction and the point of slip. The belt weight is b and the thickness is T. The belt mass per unit length is M. Centrifugal force ds can be expressed as ds equal to this equation, M2, and centrifugal force equation. Okay, mass equals to radius equal to the contact angle equals to radius equals to angular velocity, where b is the belt speed. Summing force readily becomes this equation. Okay, this equation. So what is this equation? Figure 17.6. You just take in theory, just take, okay, from the whole belt, okay, from the whole belt, just take one portion of it. Okay, take one portion of it. Okay, and then you make an equation between it. Okay, you remember when in mathematics class, in trigonometry class, you learn about this angle. Okay, they have a normal force, there has a tangent force, normal force, and everything. Okay, and then have a friction, that is called friction dn. Okay, dn, because this is the differential equation dn, and the force acting, because it is a centrifugal force, the force is at below. Okay, the force goes below and up. Okay, so this is the ds in that the range of if the movement of the belt. Okay, so in higher order term, we have dn equals to f d theta minus ds. So it is a normal force force you can refer to here, where is the normal force acting here. Okay, and dF equal to friction dm and everything. Okay, and this is the derivation. Df equal to over d theta minus f friction of force equals to negative friction m r radius. Okay, and angular velocity. Okay, solution is non-homogeneous. The first linear differential equation is this, and then at the end of the angle of rod theta, the tight side, you will have this equation. Okay, and you can write this equation and become this equation, and now FC, okay, FC equals to mr power 2 r w angular velocity power 2. So FC is found as follow, with n being the rotational speed in revolution per minute. If you of the pulley of diameter d in inches, the belt spread is V equals to pi dn per 12 in foot per minute. The weight of W, the weight W of a foot belt is given in term of weight density, okay, in pound per inch, as W equals to 12 weight density. Okay, BNT, where BNT in inches, so FC is written as FC equals to W per G over G V per 60. You get this equation. It's in inches. Okay, it's in inches. So what is C? C is FC is hook tension, Fi is inertial tension. Hook tension due to centrifugal force, and F2 equals to tension due to transmitted torque T, and D is the diameter of the pulley. Okay, so this is the explanation. When you try to understand this equation, always refer to the pictures given. You may understand. Okay, F1 and F2. This is upper force of the belt, and this is the lower force of the belt. You can see the difference is plus and minus, plus sign and minus sign. Okay, and then Fi, which is called initial tension. Fi equals to initial tension. Okay, Fi equals to F1 plus F2 over 2 minus Fc. So divide by equation 1 to equation by equation H, manipulating, it give this equation, from which Fi initial tension equals to T torque exponential F pi plus 1 minus over D. Okay, then equation 79 give fundamental insight into flat routing. If F1 equals to 0, then T equals to 0, no initial tension, no torque transmitted. Okay, meaning that the belt is not moving. Okay, the torque is in proportion to the initial tension. That means that this means that if there is to be a satisfactory felt belt drive, the initial tension must be provided, sustained, and in a proper amount, and maintained by routine inspection. Okay, so incorporating equation 79 give F1 equal to this equation, and incorporating equation 79, F2 equals to this equation. You can see the difference. Okay, difference between these two equations, and then the transmitted horsepower is given by H. H is always symbol for transmitted horsepower. Okay, F1 minus F2 V velocity minus 33,000. Okay, 30,000 in feet per minute. Okay, the manufacturer provides specification for the above. They include allowable tension FA, tension being expressed in unit of force, with the belt life usually several years for stability of flexing of the pulley, and its fact of life reflected by pulley correction factor. speed in excess 600 feet per minute in expect on life is reflected by in the velocity correction factor CV for polymer retaining belt. Use CV equals to 1 for ladder belt. You have to see figure 79. Okay, the speed factor KS is used for exclusion from nominal. Okay. Okay, this is the 17 figure 17.8 and this is figure 17.9. Okay, the velocity correction factor and everything. Okay, this is the belt velocity, this is velocity factor. Okay, applied to nominal power HD. HD is nominal power as H nominal, KS ND, where ND is a design factor for exigencies. This effect are incorporated as follow: F1A equals to BFA CP CV. Okay, so F1A is allowable largest tension in pound. B is the belt width in inch. FA manufacturer's allowed tension. Okay, CP is the pulley correction factor. You must see table 17.4, and CB is velocity correction factor. Okay, this is the steps analyzing felt bed drive. Okay, they are 1, 2, 3 until 9 step. They are until 9 step. Okay, meaning that you have to refer to many tables and do to many equation and to find the perfect belting for your case lah. And it's opportunity that many of ability data of belting from source in which they are presented be in very simplistic manner. Resource use a variety of charts, monograph and tables to enable someone who knows nothing about belting to apply them. Okay, little if any computation is needed for such a person to obtain valid result. Since a basic understanding of the process in many cases is lacking, there is no way this person can vary the step to obtain better design. Okay, so incorporating the available bed drive into form that provide a good understanding of bed mechanics involves certain adjustment in data. Because of this, the result of analysis is presented here will not correspond exactly with those from source they are obtained. Okay, so this is among the problem. Okay, then the moderate variety of belt material, with some properties listed in table 17.2, they are sufficient for solving a large quantity of design analysis problem. Okay, so the value given in 17.2 allowable bed tension are based on a belt speed of 600 felt feet per minute. Okay, you can convert to meter per second. How what is the speed? Okay, for higher speed, use figure 79 to obtain CV values for ladder belt. For polymer urethane, use CV equals to 1.0. Okay, the survey factor KS for big bed drive is given in 17.15. Section 73 are also recommended here for flat and round bed drive. Minimum fully size for various belts listed in table figure. Okay, you can read all the whole thing lah, kan? Okay, this is among the tables given. You can see the table 17.2, properties of some flat and round bed drive. You can see what are the information given here. There are the material made from leather, polymer, urethane. Okay, and there are the specification: 1 ply, 2 ply. Okay, size, minimum pulley diameter, allowable tension unit at 600 feet per second, specific weight, coefficient of friction. Okay, coefficient of friction. This is among the guideline given by the textbook, also taken from industry. Okay, this is table 17.3 for minimum fully size for flat and round urethane belt. Okay, for belt style, ratio of pulley speed to belt length. Okay, so this is the ratio, so that it can give you some guideline what are the belts that are suitable for your case. Okay, and this is the correction factor, pulley correction factor CP for flat belts. Okay, for the small pulley diameter in inches material, this is for more pulley diameter. Okay, leather and polymer, and this is the crown height and ISO pulley diameters for flat belts. Okay, ISO pulley diameter, crown height, ISO and everything. And okay, example. Okay, we continue in the next video lah about examples. Okay, that's all for the video today. Just practice about the equation uh, until you understand lah. Okay, that's all. Thank you very much.